Thanks, everyone. Thank you so much. I'm glad to see that there's so much interest in my text editor that I wrote called Spark that used MongoDB. Welcome to Machine Learning with MongoDB and Spark. We're going to be talking about quite a few things, actually. I used to be the product manager for the Spark Connector and also for the BI Connector. How many people have used the BI Connector at all? OK, cool. How many people have used Spark? A little bit? Great, fantastic. And so actually, in this demo, we're going to be demoing MongoDB, Spark, of course, machine learning algorithms. We're going to be using the BI connector, and we're going to be using the aggregation framework. So there is a melange of technology that you can impress your friends at parties with once you see this. OK, so let's dive right in. We're talking about MongoDB and Spark. So it's good to see that we have people with degrees of familiarity with Spark. Out there, it's still, what I find is Spark is a new enough technology that people are still kind of cutting their teeth with it. There's a need to explain a little bit about it. I get a lot of questions from people about what Spark is, whether it's a complementary technology or a technology in competition with MongoDB. So I wanted to take just a moment to talk about how the two systems work together. Number one, Spark is a system for parallelized processing. Well, it's a framework for processing massive amounts of data for virtue of throughput. It's optimized for throughput of data processing. It doesn't necessarily mean that it's going to be a real-time system. It's an offline analytics system because you're going to be processing a large swath of data. Sometimes you're going to be applying the same operation or set of operations to all of your data. So this is why it's optimized for throughput. MongoDB, like Spark, is a distributed system, but it's a database, right? So the domain in which these two data processing or data management systems live in are essentially two separate domains. One is coarse-grained operations, which would be Spark, large processing of analytics. And MongoDB is fine-grained processing, where we're talking about a record, a document, or a set of documents, as opposed to all records or all data in the system. Some of the things that I also want to do here is that with Spark, it's a broad area and topic. It also involves some overlap with Hadoop. And how many people have used Hadoop? Yeah, and you live to tell the tale about it, right? OK, great. So there's a little bit of level setting that I want to do because I've found that every time that I talk about Spark or processing and stuff like that, there are some people that are coming new to this talk, and then there are people who have lots of experience in machine learning. So the first thing that I want to do is that there's going to be there's going to be something for everyone in this talk, but I do want to level set to help those people that are starting to learn about Spark to come up to speed with those that may have more experience. So for those of you who know quite a bit about Spark, who've been using it, bear with me as we level set. I promise there'll be good stuff for you, but hang out with me for a little while as we get other people up to speed on this. You might as well laugh. The jokes aren't going to get any better. So again, to go back to this idea is that Spark is for offline processing of large amounts of data sets. It's not typically feasible to do a lot of great deal of processing in Spark that you would consider to be real time. Here the expectation is that the latencies are greater, but the amount of processing that you're doing is over a large amount of data, whereas MongoDB as a database is fine-grained operations. Spark also comes with a few interesting features, of course. Most prominent among them, the ones that I find most interesting, are the IBM ML libraries, the machine learning libraries that are part of the Spark API. And you would use for multi-pass algorithms, processing, clustering, learning from data sets, doing training, modeling. MongoDB can be used, of course, with analytics through most notably the aggregation framework. But as the titular name of the framework, aggregation framework, would tell you, the kinds of processing that you're going to be doing in MongoDB is aggregate functions. We're going to be doing sums, counts, groupings, averages, that kind of thing. If you are using Spark to do sums, aggregations, and counts, while you can do that, that's perhaps not the most efficient use of Spark, right? That is something that you'd want to take that processing and do it in the aggregation framework. It'll be almost certainly faster and more efficient to do an aggregation. But in the case where you're doing things that involve machine learning or extremely massive processing, or perhaps integrating your MongoDB layer or system with an HDFS cluster data lake integration, that's where you want to have, you want to use Spark. Again, it's like we see people get really excited about using Spark to do counts. And it's like, well, that's cool, I guess, but that's a little bit overkill for something that you would be more performant and reliable and cheaper just to do in MongoDB. So Spark is again, a system for this massive parallel processing. Whoops, I forgot I had this slide. There's for the test that's coming later, here are the Spark notes that you want to, Spark notes, see what I did? I told you when the jokes weren't getting any better. Yeah, so the idea here is that there's going to be on the Spark side parallelism, where you're creating a great number of processors, Spark workers that are going to be consuming this data, performing its operations, and spitting out the output. Stream processing is also part of the libraries that are interesting that come with the Spark API. But then, of course, in MongoDB, we're doing native processing. Data never needs to leave the MongoDB realm to get your results as long as you're doing aggregate functions, which a great many people do. Another question that I often get is, what's the difference between Spark? Is Spark effectively replacing Hadoop? I think, in my opinion, that Hadoop is itself a framework that involves HDFS, that involves not just the HDFS layer, but also the map replace APIs that many people from maybe 10 years ago would be familiar with. The thing with the difference between Spark and Hadoop is I feel that Spark is easier to deal with. It's got an API that's a little bit more intuitive. Certainly the documentation over the years is much better in Spark, so it's easier. The learning curve for people coming up to speed on Spark is higher. Spark is also generally more performant than vanilla Hadoop because Spark uses caching. You can have selective caching. So caching is, we have a data set that we're going to be processing in Spark. I'm going to be doing multi-pass algorithms, as we'll be demonstrating a little bit later in this talk, like a clustering algorithm, or I'm going to be doing classifiers where I'm training a model. Because I'm going to be processing the same set of data in a multi-pass fashion, it makes a lot of sense for me to cache that. And Spark provides a caching function in the API that allows you to do that, to cache selectively data into the system so that you don't have to keep going all the way back down to disk, which vanilla Hadoop had done and suffers the performance consequences of that. Every time you want to make a pass over your data set, you have to go to disk and you suffer the time and penalties as a result. So Spark is pretty good in that sense. Now, interestingly enough, you'll notice that I said that Spark is easier. It's not necessarily, the API is sophisticated to a degree. What I found is that we're dealing with distributed systems, which by their nature are a little bit more complex than single process. It seems obvious, but that sometimes comes as a shock to people that are making their dive into distributed systems. There's a level of sophistication and complexity that's a little bit higher. Is it easier than Hadoop? Yes. But one of the things that I found is that Hadoop, before Spark, 10, 12 years ago, was very buzzy itself. It was a panacea for a lot of people, a lot of shops. And one of the places that I worked at before, we were trying to do a lot of analytics, and the C-level execs would think of it in terms of we just need to get more of the Hadoops, right, to solve any data problem that we had. So the promise was very high in Hadoop, but the implementation was difficult. People had a lot of trouble with it. So just like Hadoop, you also see that Spark has this kind of, it's going through that buzz phase of, it has that enthusiastic adoption phase, you know, we talk about, and then it crests where people start using it, and then it goes into a trough of disillusionment, which is the kind of the area that Hadoop goes to. And I want to save you from that. Incidentally, trough of disillusionment was the same name as my punk band in high school. So, some interesting things about Spark. It has an interactive shell the easier API, but you need to know what's going on, and it has the selective caching. So that's what we got going. And it also provides multi-language support, APIs for different languages, of course. I'm a dyed-in-the-wool old Java guy. I've been playing with Scala, which is a lot of fun. The demos that I've written are in Scala. And then, of course, there's a Python API and an R API. From what I see, it seems that Python is winning out the popularity for the analytics languages. How many people are Python favor? How many people are R favor? Yeah, you're out there. It's good. A secret cabal of people that still hang on to R. But it does seem like that Python is winning the wars on this one. But it doesn't matter. You're all developers here that we support. So let's talk a little bit about the ecosystem, about Spark, Hadoop, and MongoDB. A lot of what I find people have trouble is that Spark and Hadoop, they're kind of related to one another because they share components of each other's ecosystems. And core to that is HDFS. How many people who wants to win points in MongoDB, the home game, what does HDFS stand for? Can anybody say? That's right, Hadoop Distributed File System. That's right. So what I want to do is just go through a little bit of the word salad that is the ecosystem and hopefully clear things up to set you on the right path. For those that are familiar, again, you'll see how these things, you already may know how these things work. For those people that are trying to understand, my goal here is to set you guys up so that you can go home and try this at home and start developing more sophisticated things. But what I find is a lot of people get confused about this arena of all these different frameworks and what do they do, and I don't understand, and you kids today with your rock and roll music. So Spark, the name of the game is to process lots of data, process big problems. So how do we handle big problems, aside from panicking? We take big problems and we break them up into a set of smaller problems. So we're going to distribute the problem. We're going to do distributed processing in parallel with Spark and MongoDB. So to do that, number one, the first step is I have to distribute my data across a number of nodes. I'm going to split the problem up across a number of nodes. And that is the first layer in the Spark universe. The Spark Hadoop universe is HDFS, the distributed file system. Distributed data for managing distributed problems. Outside of that, if I'm going to be processing all of this data across a distributed system, I need a system for managing the resources I have in aggregate across all of these systems. So if I have 8 Spark workers, how much RAM do I have in total? How much CPU do I have in total? Am I overutilizing one? Am I slamming one server while another one sits idle? Right? These are big problems of distributed systems. So the Spark framework provides this next layer in the shell. Once I've distributed my data, I need to manage my distributed resources. And that's what this layer is. So how many people know what YARN stands for? Yes, yet another resource negotiator, right? It negotiates the resources that we're going to use to process the system. And then, of course, the YARN stuff comes from the old school MapReduce days or MapReduce 2, version 2 of Hadoop. But on the other side, we have the Spark standalone system, which is a great system for prototyping and learning. And then you have Apache Mesos. Some people call it Mesos, but they're wrong. And these are distributed systems. Mesos is for more, by now I would imagine that a lot of people are familiar with Mesos and similar technologies like Kubernetes. And Mesos is a more generalized system for handling distributed resources where YARN is more focused on MapReduce. Okay, outside of that you have the distributed processing API. Okay? Now again, to show you where this universe lives, on the left side is the Hadoop API, which is MapReduce focused, centric. And then you have the Spark API, which I feel is a little bit more rich, easier, featureful, better. But you can see also that Spark also uses YARN as a resource negotiator on this in this kind of system. Spark, as you saw, it has APIs in these different languages. Hadoop is Java focused. I don't spend too much more time in Hadoop myself, so I don't know if they've bubbled up to different language APIs, but it's Java, right? So a lot of people have trouble with Java. I don't know what their problem is, but not every analyst will be using Java. Towards that end, there's this last layer that I want to talk about, which are essentially a DSL layer, domain-specific languages. And this is where we see systems like Hive and Pig. Pig is a high-level language for I don't know, how many people use Pig? That one's, yeah, it's declining in popularity. People always think this is part of the joke, but the language for Pig is called Pig Latin. But I mean, that's really what it is, but it's going out of favor very rapidly. These are high-level languages for use of people who are not familiar with Scala, not familiar with Java, maybe not so much in Python. They need to do work. This is not their language in their domain expertise. They're not, they're good analysts, but they don't know those languages. So these higher-level languages that abstract some of the API in interesting ways. So you have Hive, or HQL, which is Hive Query Language, which is a variant of SQL. And then you have Spark SQL. And you can, again, impress friends at parties. Hive and Spark SQL is the same language API as Hive. They're essentially the same syntax. And then you have the streaming APIs that allow you to do real-time stuff, as well as the Spark shell. I kind of put that on the outer layer of the Sparkverse. The Spark shell is the interactive stuff that we've got going. OK, how do these things all fit together with MongoDB? Any guesses where MongoDB would fit? Outside, in the inside, right smack in the center. There's a good guess. Because what we want to do, the value of using Spark and MongoDB together is that we want to utilize these machine learning algorithms. We want to utilize the capability to parallelize the processing. But we want to manage our data in MongoDB for a number of very good reasons. So MongoDB would fit in the center where the Spark system would either be pulling data out to process and or pushing the result sets back into MongoDB to be used. You can actually use the Spark connector as a bridge from your HDFS cluster over into MongoDB or move data out of MongoDB into the HDFS cluster if you wish to through the Spark connector. There's no reason that you can't do that. I prefer this mode because if you think about it, if you're able to take data out of MongoDB, process it, and push and let's say this is your operational database. This is a database that's in service to your business layer, your real-time business, highly available business systems. You're pulling data to be processed by Spark, pushing the results back into the same database, making those analytics available to whatever business processes that are currently live. So the domain that I was in was real-time bidding. So the efficiency of my bidding algorithm was limited by the fact of how much time it took me to get data out of the frontline database servers. This was before MongoDB, back when the Lincoln administration and everything was in black and white, and we used to drive cars with our bare feet back in the old days. Yeah, bad jokes. Anyways, we had to pull that data out, ETL it into a separate system, process it, get those analytics back into the system. It took hours, actually, to operationalize that data. And the ETL systems would break. Where you get your efficiency in this arena is that you're eliminating ETL. You're eliminating layers of ETL, which are going to be the first thing that break in any distributed system. Michael Nygaard had a good book, just a plug. It's called Release It. How many people have heard of Michael Nygaard's book, Release It? Great. It's excellent reading. Anytime that you have two systems that are ETLing, that's where things are going to break first. So if you eliminate that, you get speed, you get efficiency, and you get a reduced complexity of your distributed system, which is beneficial. Now, one thing that might strike you is that while Spark is a new technology, there's a lot of interesting things that it's a system for deriving what's going to happen into the future. These are things that we visited in the past as human beings before, to predictive analytics and machines for. No, I just thought it looked like the Aztec calendar there. Edit that one out. Note to self. OK. So actually getting the Spark connector, we publish it. It's open for you guys to use today, this moment. in GitHub under MongoDB/Mongo Spark. It's maintained by our Spark team. The main contributor is a gentleman named Ross Lawley, who's with us today at MongoDB World. Excellent programmer, excellent developer. And you can use it right here, the Spark Connector, and contribute to it if you like. It's also a fun open source project. So that's what we're using. That's where you get access to it. The APIs that we're going to be using for machine learning are also published in the excellent documentation of the Spark API documents here that you see here as well. And we're going to run through a k-means clustering algorithm today. I thought that would be fun to do. It's a pretty kind of an easy piece of machine learning to use if you're new. And the API guide is right there. It's well documented, shows you how to use these systems. There's lots of people using them as well. So in conjunction, you have a lot of support with just in documentation about how to use the system. Let's talk about clustering algorithms as we transition now into actually using the Spark connector to do some useful work. Clustering algorithms, the reason I picked this as a demo is there's essentially two kinds of machine learning. There's supervised and unsupervised machine learning. And guessing about where people are with machine learning, I wanted to do an unsupervised system. Clustering is an unsupervised machine learning technique system. Supervised learning means I have a training set of data that represents the kind of data that I'm going to be encountering sometime in the real world. But this is a sample of what the real world looks like. Now I'm going to take my supervised learning algorithm and I'm going to focus it on this training set, get it to start learning and create a model, which I will use to process all the data out there, which I expect to look very much like my training model, my training set. That's supervised learning. Clustering is unsupervised. Clustering is a way of discovering potentially what groups of information or characterizing information that you might want to identify as a training set to go on to more sophisticated machine learning algorithms like naive Bayesian classification. Clustering is kind of easier to deal with if you want to be learning how to do the API. Kind of the examples that I've defined here is not so much to do crazy analytics as much as understanding the API so that when you go home, you can prepare for the test that we'll be sending to you via mail and learn the API. Okay, so clustering algorithms. How many people are familiar with clustering algorithms? Great, terrific. So clustering algorithms is we have vectors. We're going to be analyzing data that is an n-dimensional vector. We want to find out groupings of data points together. People most typically think of it in spatial terms. That's the canonical way of describing a clustering algorithm. I see a two-dimensional field, and I see clusters of points that I can identify. So one way is to say how many teams are on the field right now in this system, right? 2. How could you tell? Because as a human being, you can see that there are teams clustered together on either side of a line of scrimmage. We understand that there's 2 teams on the field because we can see that they're grouped together. There's a cluster of 2 groups. Harder, though, is the idea of how many clusters do we see at this time? 2 is the answer, of course. But the spatial distinction, the spatial separation of these clusters, these teams, is less distinct. How did we know that there are 2? Colors, yeah, that's right. So that is to say that the reason that I use this analogy is that people get hung up that clustering only works on spatial dimensions. Clustering can, of course, be used in any dimensional space. Another prime example of clustering is that you would use stock market data that you process together to understand what set of businesses or corporations, public companies may be similar to one another, that are grouped together. Not necessarily that they live in the same industry, but they share common characteristics and therefore they cluster together as well. So that's kind of the idea here, beyond spatial thinking. K-means clustering is a specific form of clustering algorithm. How many clusters do we see in this example that we're looking at here? I do have to say I cheated on this one because I pulled this one. This is from a Wikipedia Commons art. But it was good. I mean, it shows a clustering algorithm being executed, and I couldn't improve on it, so I figured steal from it. How many clusters do we see here? 3, in a kind of a Mickey Mouse shape. We as human beings, of course, are very good at understanding seeing the clusters that we're having here. Machines have to apply an algorithm to it, a heuristic. So what we're seeing here is that in this particular case, the way that a k-means clustering algorithm works, which is important to understand how the demo is going to work, is that we have selected that we're going to try and optimize for 3 clusters, right? This is a centroid-based clustering algorithm. So what happens here is that we say, okay, we're going to have 3 centers of a cluster. We're going to look for 3 clusters, throw those centroids just randomly somewhere in the two-dimensional field. Bingo. Now, group all of the points that are closest to where those randomly set centroids are and say that's your cluster 1. Now, move the centroid to the center, the geographic center of those clusters that they're assigned to, rinse and repeat, rinse and repeat. And you'll see that initially we're in iteration 14. Now we're at the start. You'll see that the clusters start to coalesce, that we see that there's a red cluster on Mickey's right ear, and there's another cluster on Mickey's left ear, and then in the center is the yellow cluster. They coalesce until we find the clusters if we're looking for a 3-centroid cluster sooner or later. We're going to be doing that today in our demo as well. You can see that this is this a single pass algorithm or a multi-pass algorithm for people who want to score more points for beer tickets tonight? Multi-pass. There's too many right answers. There's no beer pass. I'm not sacrificing my drink tickets. Anyways, yeah, that's right. It's a multi-pass algorithm. So what's important is because we're going to be reprocessing these data points, we want to use the internal caching system of Spark so that we don't have to keep reaccessing the data. Okay, so we're going to be using data that's been provided by the National Oceanic and Atmospheric Administration, NOAA. That's available to you on Data Refuge, which is a system, it's a nonprofit organization for preserving climate data in case our political environment changes such that people start deleting non-politically expedient scientific data. And that's what they do, so I got to give them a little bit of a shout out, and it's a good repository for data sets. And what we have here is that we have in the United States, islands, territories, is a set of weather stations that are deployed across the United States, and they're collecting precipitation data. Some of them are collecting wind data and stuff like that. But it's a nice big data set that we can perform some clustering algorithms on. What's going to happen here is I'm going to try and figure out where storms would be on a given day by using a clustering algorithm, presuming that if they're geographically close to one another, and the precipitation level is generally about the same amount, that's a storm. I can say that a storm is being detected among these contiguous stations, right? If I see a separate storm with in a different location but has the same precipitation level, the geospatial distance between them would tell me that they're different storms, right? So I'm actually going to cluster on this is going to be a vector, 4-dimensional vectors. Precipitation, elevation, latitude, and longitude, right? And what I've done here is I've selected, just because I think it's funny, no. My best guess is I'm going to try and make 5 clusters, right? Let's see if there's 5 storm systems that we can see in the United States. And I'm going to do about 20 iterations, go over the data 20 times to refine the definition of my 5 clusters. Perfect, thank you. The weather station data that we've collected from these stations is really simple. This is actually the station data. This is static data that describes the location, the name, the characteristics of the station data. I'm going to store this in one collection in MongoDB. This data rarely ever changes unless the station goes out of business or something like that. These are fixed stations, so this is my fixed data, right? I only need to refer to it really once. And the information that I really need from that is the latitude, longitude, and elevation, the fixed location of these stations. The actual data that's coming in, this would be more like an event or a log or IoT. I'm going to pack as many buzz terms into this talk as I possibly can. An IoT-based event sourcing system where I'm recording logs from these individual stations. Every 15 minutes, they report in the cumulative precipitation data that they've collected. And this is what it looks like. This is how I'm storing it in MongoDB. A very simple record, right? And the thing that's most interesting to me is, of course, the value down second to the bottom. In this case, this station recorded 0 precipitation for the time period of 2500, which is the daily total. Okay, so those are my two collections in MongoDB. I have the station data, and then I have the per 15-minute log information for each weather station in the United States. Every 15 minutes, I get a report, and then a daily total at the end of the day. To use this data, I'm going to run the Spark shell, the interactive shell, which is what you're going to see here. And what I'm going to do is I need to configure Spark to do a couple of things in order to use MongoDB. Number one, I need to tell it where the database is, its data source is. So you see the configuration parameter Spark MongoDB input URI. That tells Spark where to go to get what data. If it's .input URI, input data. This is where I'm going to be reading from. Now, I want to write my results of my analytics, what the cluster definitions are, into the second parameter. This is where I want you to write to, back into MongoDB, into a collection called cluster within the NOAA database. And then finally, the last thing I need to do is tell it where to get the Spark connector. And the cool thing about Spark is that when you pass it as a configuration, it uses the Maven coordinates to download this directly from the Maven repository. So it makes the management of these libraries much, much easier. And if anybody's had to distribute libraries across a distributed system, that's a major pain. Nice convenience to have here. OK, so let's have some fun and demo this thing. Let's go over here. Whoops. Let's go back. Kill that. Whoops. And I'm going to go start that up. Spark is going to initialize. Let me pull over here and grab I'm going to do a little bit of cut and paste demo time here. I'll post this stuff for you to play with as you like as well. Grab this stuff and run it in. So there's a little bit of prep. Actually, let me go up here because this is interesting. If you look over here, I'm creating, this is in Scala, so for some people this might be a little bit weird, but you'll see here I'm building an aggregation framework pipeline. This is actually an interesting feature of the Spark connector. I don't want to pull all of the data from MongoDB to be processed. I'm only processing April 1st, 2013, spring showers, right? I want to see a good day with lots of rain in it to process this data. So a convenience of the Spark connector is that you can pass an aggregation pipeline as a pre-filter into MongoDB so that I don't have to draw the total amount of data out of MongoDB to be selective in Spark. I can do that if I hate myself. It's much more efficient to pass a filtering operation to the database, and I'll get that selected set of data back for processing. Then down here, I'll do a little bit of changing it, remodeling the RDD in a preparation to be processed in the k-means algorithm. And you'll notice that I'm also using another aggregation framework feature here, $lookup, which is the left outer join operation in MongoDB. So I'm joining the station data with the input, the registration of how much precipitation was. So let's go ahead and run this thing. And at the very last part, once I finish my processing, I'm going to save the results, if you can see at the bottom there, back to MongoDB. The magic happens right here in this line. Whoops. The magic is right here. That's the kind of the cool thing about the API. I say k-means.train. I'm not really training the model. I'm actually processing the clustering algorithm. And I'm saying I have a vector of all of the rain data that I'm coming in, that four-dimensional vector. I have a series of vectors in this space that I'm going to pass into the k-means algorithm. I'm telling it that I want 5 clusters and I want it to iterate over these points 20 times to refine the definition of the clusters. I go and execute this and save it into MongoDB. So here we are. Nice ASCII art tells me that Spark's up, and I'm going to start processing the system. Now, like a baking show or a cooking show, this thing is going to load. It's going to process, right? We got it. Now it's going through and it's performing that iterative series of stuff. Like a baking show, I just put that in the oven. I'm going to take my pre-cooked stuff out because we don't want to wait for a log line cursor go around and around for this to happen. Here's, once it comes out, we can go over to MongoDB and take a look around. Actually, let's do one better. Now, I told you that there was going to be, this is what it looks like, the output of this clustering algorithm here. What I'm using in this combination of stuff is I'm using the BI connector to connect up to MongoDB to present the data in a format that Tableau can understand, right? And I use the data visualization features of Tableau to automatically map this against the United States, right? So I told you there was going to be a lot of technology used in concert here, and so I've used the Spark connector with MongoDB to perform machine learning. I push my results back into MongoDB, right? Use the BI connector to present that as a SQL interface so I can leverage my Tableau stuff. How many people use Tableau or other data visualization stuff? Great, terrific. So now I can use a data visualization tool that I'm happy with. All right, that is the demo. So in a way, the trick is that there's not much to it except to do it. So that on that anticlimactic note, that's it. I don't know that I've left a whole lot of room for questions, but I can be out in the hall too if you want it.
Yeah, we've got about 3 minutes. We've got three minutes. The good news is there isn't something immediately following, so I don't have to get kicked out, but I know people will start leaving, so it'll make it tricky. So let's try to do 2 quick questions if we have it, and there's a lot of like campers, so I'm not sure if I can make it to you, but if you can say it loudly enough, fired it off.
Can I add more than one input sources for MongoDB in the Spark connector?
Yes, the question was, can you add more than one input source in the Spark connector? Yes, you can. So you could draw from multiple collections. You could draw from HDFS and MongoDB. It's a hub. You can use it as a hub kind of a system.
With change streams and structured streams within the two, have we put those up yet?
That is a demo that I've been wanting to do for a little while, but I just haven't had enough bandwidth to use change streams with the Spark connector for streaming and stuff like that. So come back next year.